All right, so we're down to the third chapter here. There's the schedule, and I've got a lot of things filled in now about the projects. I wrote a lot more of the projects and set due dates, so we're set for a while. Due dates over here on the left. Anyways, today we're going to start chapter 3, and I imagine probably finish chapter 3. I'll probably just do more demonstrations next time. We'll see. But I think chapter 3 isn't that long. It's getting down to the meat of it here, though. These are those more relatively advanced algorithms that you probably did not cover in a beginning programming course, and that give you interesting, powerful techniques. Brute force is obvious. Brute force is where you just try every option of something, and recursion is more important, and divide and conquer. I'm going to be using a lot in the projects, and then we'll talk about these other ones like greedy algorithms. So brute force is the simplest way to hack into things. Use it to crack cryptographic keys or passwords, or in general any problem. But the most common case I think of is cryptography, where you try to get into some encrypted stuff without a key. I see this all the time on TV shows. It is a popular belief, unfortunately, by people who should really know better, that every cryptographic algorithm can be cracked if you have enough time. And that is absolutely false. In a sort of philosophical sense, it's true, but the whole point of cryptography is to choose algorithms where that time is longer than the age of the universe. And that's true of all the modern cryptographic algorithms. We wouldn't use them otherwise. So anything encrypted with a modern algorithm, you are not getting in without the key. That's it. Nobody's getting in without the key. However, other things you can try, all possible moves. And if people are using an old, weak algorithm, you might be able to try every possible key. And certainly when you're trying to guess a password, you can get in if the person didn't choose a rare password, because there are dumps out there of the billions of passwords. So you can easily take the top 1 million passwords. And if you're using extremely weak cryptography like Microsoft Windows uses, you can literally try 100 million passwords in a reasonable amount of time. It is a disgrace. Microsoft's password hashing scheme was obsolete when they developed it in 1993, and they've never improved it. Linux figured out how to do it right in 1975, and Microsoft never got the memo. Anyway, so that's brute force. In principle, it's effective if you have enough time. And so this is what you often have to do when you're searching through. If you're searching through data and the data is not sorted, then there's nothing you can do but a brute force search. You start with either the first one, second one, third one. There's no order, so there's nothing faster. And you'll see, here's an example of a brute force. I have a haystack, and then I'm looking for a needle in the haystack. So I put random things in the haystack, and then I keep track of the time, and then I look to see if the needle is in the haystack. And you see if it's 100,000 items, it takes 0.07 seconds. If it's 1 million items, it takes 0.7. If it's 10 million, it takes 9. So if I increase the length of the haystack by a factor of 10, the time it takes goes up by a factor of 10. Approximately. There are always some other contributing factors, so it's not a perfect factor of 10 there, but it's close enough that you see that's scaling complexity of order n, like we talked about before. All right, that's the code to run it live. I'm not going to bother. All right, so recursion, however, is one where it's much harder to figure out how long it's going to take, and this is only relatively advanced languages let you do this, but Python is one of them. So if you want to determine a factorial, and this is mathematical recursion, so if you're taking 0 factorial, the answer is 1. Otherwise, you take n times the factorial of n minus 1. So this function calls itself. So to calculate the factorial of 4, it has to calculate the factorial of 3, and to do that it has to call the factorial of 2, and the factorial of 1, and the factorial of 0, and then it combines them all to get back up here. Now this works. It's easy for the programmer to program. It's relatively easy for a programmer to understand, but it's a lot of work for the computer. It has to call itself. It's going to end up with a stack of 5 factorials all running at the same time. And like I say, this is a recursive function where you're allowed to define a function in terms of itself. And sometimes this can be a real mess, and I caught my attention because in the 1970s, when I first came across this stuff, my roommate was taking operating system design, patching operating system and stuff, and he taught me about Ackermann's function. And Ackermann's function is famous because even though it's recursive, it is monstrously difficult to calculate. Because the way, now if you take a look at the factorial up here, and you'll see this is the most common recursive case you see in mathematics. You want a function of n, and you define it in terms of function n minus 1. So all you have to do is go to the previous one and the previous one. All you have to do is do basically complexity n. But Ackermann's function is maddening. It's got two functions, m and n, and so that depends on Ackermann m minus 1, 1. Now that would be like the previous one, but it also depends on Ackermann n minus 1, and this is Ackermann's function here. This n parameter did not even go down necessarily. And that's what happens when you try to calculate Ackermann's function. I tried to calculate 0, 0, 1, 1, 2, 2, 3, 3, and I can only get here. And notice how it goes up, 1, 4, 7, 2, 4, and 400. In order to calculate 4, 4, you have to get Ackermann's function with a 12 here. And that's 11 and 10. And each one of those is going to call more. So it grows monstrously fast. And what my friend told me at the time, we had the entire college ran on one state-of-the-art IBM mainframe, and he froze that entire system completely for several hours, calculating Ackermann of 5.5. That used up all the computer resources for hours at the college, and then they had his one printout with one number as a result of all that, because it is extremely complicated. It grows ridiculously fast. Yeah?
So, you said that was the 70s?
Yeah.
How, is it any faster now, or is it still?
Well, computers are much faster. However, my Python can't go above this, then it crashes. When I run this in Python, it crashes, not because it says you can only have you exceed the buffer of how many functions you can be running, and that limit is like 1,000 or 10,000.
So would that be like a runtime error, or?
Yes, it's a runtime error, and it tells you you've exceeded the number of allowable instances. And you can even crank that up, but it started at 1,000 or so. I'm not sure I'd be able to get A of 4.4 with any amount of resources that Google will give me for free. That's it. It consumes a huge amount of memory. I think I hit the memory limit. You can, because remember, you have all these functions. Like, go back to here. To calculate factorial of 4, I had to have 5 copies of this in memory running at once. And to calculate Ackermann's function of 4, I had to have more than 1,000 of those in memory at once, and that's it hit the limit. So it's pretty crazy.
So recursive functions are quite resource intensive.
They use a lot of memory. I think that's the only resource they absolutely necessarily use is a lot of memory, because you call it once, but then it calls itself a bunch more times. So one thing it certainly does is use a lot of memory. Now it might waste a lot of CPU, which I think is the next topic here. Yeah, well, we'll get there. But all right, so divide and conquer is really important, and I've already mentioned the binary search several times in the projects, and it's going to come up. This is really enormously powerful, the binary search. So if you sort the elements before you search, you can suddenly search much more efficiently. I'm looking for 4. All you do is look in the middle and see is it above or below that number. If it's below, you throw away half of it and keep this half. Then you guess the middle again. Is it above or below that number? You throw away the wrong half. So every single guess divides the list in half. So this is the fastest search, or I should say it's the almost fastest search. It's the fastest one in your book so far. There is a faster one, which is Bloom's filters. Yeah.
So how does it guess for?
Oh, well, this is what you're looking for.
Right.
So you're given a list, and you're given a number to find in that list. That's all. And so you just compare that to the one in the middle, and that cuts the problem in half. And then you compare it to the one in the middle again, and that cuts the problem in half. So every single guess cuts the list in half.
I see.
So it's only going to take the logarithm of the number of guesses. You don't have to compare it one by one while going through the list, which is the brute force search, which is what you would have to do if the list was not sorted. Because it's sorted, you can be much more efficient. And so that's the binary search. If it's sorted, you test one value in the middle. The needle key is either above or below that, and the remaining list is half the size, and now you just repeat that over and over. So here, we do a binary search. Here's the haystack, here's array, here's the start and end points, and there's the key. So we start and end here, which would normally be the first and last element in the list, and then we just move. Find the midpoint. If the mid equals the key, we're done. We found it. Otherwise, if it's less than the key, then we want to be on the left side. If the key is greater than the mid, then we want to be on the right side, so we move the start up to the middle. Otherwise, we move the start over here. Either way, we cut the list in half. And that's why I say this is scales as log of n, which is very nice. Now, Bloom filters, which I haven't yet put in the project, scale completely independent of the size. They're fantastic. I may add them to the project. Like I say, you can hear all about them if you listen to Security Weekly about 2 weeks ago. There's a whole show explaining them. They are wonderful. And they're constant no matter how many items are in the list. and they're used a lot in computing. I'll probably add them to the project a little later, but the binary search is fast enough to make a huge difference. So here, I made one that will try perform each search 10 times and print out the total number of steps required to do it, and I should have the answer. Yeah. So here we go. A list of 1,000 takes 83 steps, 10,000 takes 124. Each multiplying it by 10 takes about 30 more steps. So you see, it hardly grows at all as you get bigger. It grows by a constant increment of 30 every time you multiply the list by 10. So that's pretty good. All right, and that's the code that does it. All right, and related to it is the merge sort. So you can sort things by using the same kind of logic. Divide the list in half, keep going until every sublist has only one element, then merge them in order. And repeat until there's only one sorted list. So if you have a list with numbers out of order like this, you just cut it in half, and then you cut it in half again, and you cut it in half again. Now these are all completely lists of one. Now you merge them in order, and merge these in order, and then you have to have a merge function that can take a list and another list and merge it, putting them where they belong. And what we're going to see, this part takes log n, but this part takes power of n, and you end up with n times log n is what it takes. So the merge sort part is what splits the list in half recursively. And so you see that here. Here's merge sort on the list, and here it's composed of merge sort of the first half and merge sort of the second half. So this function calls itself over and over and over as needed. And then when it's done with all that, it's going to merge them all. So you're going to have, again, a pile of these in memory with a number of copies of this function in memory equal to the log of base 2 of how many items there are on your list. Yeah?
So for the recursions, would that be about 3 or 4 stored recursions?
Copies of the function?
Yeah.
It would be 4 for a list up to 16. For a list of 1,000,000, it would be 20, and so on. Because you take the log to the base 2.
Yeah.
And the log of 1,000 is 10 to the base. The log of 1,000 base 2 is 10. This you'll learn a lot if you do this kind of work. 2 to the 10 is 1024. A very handy number to know. So yes, that's and the longer your list is, the more copies will be in memory, but not like Ackermann's function, where I had thousands in memory. It's just going to add like another 10 for every 1,000. So for every multiplier of 1,000. So even a huge list will not consume too many copies of this function. The list itself, though, will probably not fit in memory at some point. And then everything will slow down and you have to keep reading the list of disk. So the merge combines two sublists into one merged list, and that has complexity n. There's no way to go around comparing each element one by one to figure out where it goes. So the end result is the whole thing is n times log n. It's going to call one function n times, and that log n times the split, and that is going to call the merge function, which is going to take n times. So you end up with n times log n. And so if you actually measure the function of it, every time I multiply this by a factor of 10, this goes up by a factor of 30, which is n times log n. So 0.05 goes to 3, 2, this one's far out, this one gets bigger. There's always some noise. This growth is not as clean as you might want it to be. But anyway, that's the point. Every multiplying the list by 10 will make this go up by a factor of 30. That's n log n. All right, and then there's dynamic programming. And here we're getting back to some of the questions you've already asked. So notice if your problem is solving the same thing over and over and over, which, by the way, it will be. If you use recursive functions, you're going to waste a lot of time doing the same calculation over and over. So a way to prevent this is to save the results of the subproblems in memory, and then you just look them up instead of recalculating them. And this is the issue of time-memory trade-off, which you use all the time. You can save time by consuming more memory. And in password cracking, they call this rainbow tables. You save a bunch of data in memory with a lookup table for the hash function, and now you can calculate hashes of passwords much faster. And up through Windows XP, this will work to completely break all passwords. That's why login passwords of all Windows up through Windows XP are broken. You can break them in a modern computer in 5 minutes by using lookup tables, because modern computers have enough memory to store a table so you can very quickly try all reasonable passwords. After that, Microsoft finally relented and made a better algorithm, which is not that fragile. But anyway, so Fibonacci series, for example. if I want to calculate Fibonacci, where Fibonacci, the first number is, Fibonacci of 1 is 1, and from then on, everything is fib of n minus 1 plus fib of n minus 2, and fib of 0 is also 1. So fib of 2 is 2, and on you go. So, yep. So if it's 1, you return 1. If it's less than 1, you return 1. This is 0 and 1. And from then on, to get 2, you add the 2 before it. And you keep on doing that. So it's going to keep calling 2 copies of fib for every 1 you put in here. So it's going to have an exponentially increasing number of fibs in memory. If you call fib of 10, 10 is going to call 9 and 8. 9 is going to call 8 and 7, and so on. It's going to have many copies of it in memory, and a whole bunch of them are doing the same thing over and over. This is spectacularly inefficient. And you'll see it here. To do Fibonacci of 5, it will need to know 4 and 3. To do 4, it will know 3 and 2, so it's going to do another copy of 3, even though it has one running here. 3 is going to need 2 and 1, and this 3 is going to need 2 and 1, and that one's going to need 2, so I got 3 copies of Fib2 all running in memory at the same time, pointlessly wasting memory and CPU doing the calculation I've already done. That's the problem with recursive functions. They're stupid. You know, they just, you told it, figure out 4 and 3. Okay, the way to figure out 4 is to do 3 and 2. It's not smart enough to realize, wait, I'm already doing 3. You didn't add that to the program. You'd have to add the intelligence to do that. Yeah?
So it's kind of like, because when I said the previous question, they suggested it as like, it takes less lines, but it's, you know, it's less of a smart solution to the problem.
Well, yeah, and this is the real important issue. Everything is a trade-off. It is easier for the programmer, but harder for the computer. That's true of almost everything we do these days. Computers have gotten faster and faster, and human life is considered more valuable. So making it easier for the programmer, make a computer do more work, is okay up to a point. That's why we write in high-level languages like Python. If you wanted to really save computing resources, you'd code in assembler, which, by the way, I highly recommend. Assembler is great. Anyway, but most people don't like it. I'd rather write in a high-level language so you have an easier time, but the computer has to do more work. And you just have to choose what the best optimum is there for your problem. And what most people do is they write in a high-level language, except for certain routines that are critical, and those they write in more efficient languages, especially for things like missiles and spacecraft where real-time processing is necessary. You can't be using a sloppy high-level language where you don't really understand exactly what it's going to do and exactly how long it's going to take. Like I showed you in my examples, my Python code doesn't actually multiply by exactly 30 every time I go up by a factor of 10, even though it should. There's a lot of randomness in there because the sloppy high-level language is not as simple. Yeah?
So in those instances where you're using like another language, because I've seen it like they use JavaScript with HTML, how does it translate?
You have to code that. You call a function and you have to tell the function. Now you can put inline assembler in C and you can just make a separate file and call it, and there's various ways to do it. The way I usually do it is the incredibly sloppy, dangerous way of calling a different command line command. Going to the bash, which I've already done before. I wget a file to get the file in there, and one of the students said, you know, you could just use requests and get it inside Python, and that is a much better policy. Going to the command line is a dangerous move. But like I say, when I consulted for a big company, and they said, can you make an app that demonstrates all 10 of the top 10 OWASP flaws? And I said, you want me to write a bad app that does everything wrong? I can do that. I have that skill. And that's what I did. And it was only 30 lines of PHP, and then they said, no, you have to write it in Node. And I said, do I really have to write it in Node? And they said, yes, you do. So I turned it 800 lines of Node. Boy, I hate Node. Anyway, but they paid for it. I can't argue. All right, so here's the point. So what you do to be dynamic programming, you remember each one you've calculated. So now, when this one tells me it needs to know return value, it needs to know 2, it looks up the value of 2. And this, 2's been calculated once, next time you need it, you just look it up. 3's been calculated once, next time you need it, you just look it up. You don't waste time repeating a calculation you've already done. So that's dynamic programming. And so it means you're going to have to define, so it's going to look up here and see if it's got that function already to look up. It's going to have enough memory to store them all, and therefore it'll use less CPU and less recursion memory to go, but it does have to have enough memory to store the table of all the answers you've made so far. All right, and here's Ackermann's function. I thought it might help with Ackermann's function, so I coded it with recursion, and it still can't get any higher than 3. It crashes and burns. There's still too many copies in memory because Ackermann's function is incredibly cruel. A of 4, requires more than 1,000 copies of it running at once in memory with recursion, and I don't even know how many more. So here it is with dynamic programming, still fails. And by the way, here's the error you get. Recursion error, maximum recursion depth exceeded. That's what it is. You can only call a function can only call itself 1,000 times before Python gives up on you. You can turn that up though. I didn't try that. At some point you'll hit the limit of the memory Google gave you, but the default is 1,000. Might be 10,000, but I think it's 1,000. Anyway, all right, so now another issue is a greedy algorithm, and this I've come up a lot in machine learning algorithms like large language models. So you can suppose you have an optimization problem with many steps. Just think about, yeah, go ahead.
Actually, this is, I don't know if this would work, but could you technically make an identical function and have them call each other?
Yes.
Would
But
that would work as a loophole around that 1,000 barrier?
I don't think it would. Oh, it might not. I think it depends on how it's implemented. It might be you can only have 1,000 routines running in memory at a time. Might be your stack can only be 1,000 deep, or it might be you can only call the same function 1,000 times. I don't know which of those it is. It's a good question. I don't know the answer. Anyway, so think of the traveling salesman problem, right? You have a map, you have to visit certain cities, and you're trying to figure out which route would be the shortest total distance. This is an almost unsolvable problem. I'm sure you've come across it before. There is no efficient algorithm at all, other than there's nothing better than brute force, really. This turns out to be far more difficult than you might imagine it is. But you could do the greedy algorithm. This is probably what most people do. They just go to the closest city at every step. And if the cities were in a nice normal pattern like a loop, that would probably be the best move. So if it's really like this, you just go to the nearest one, go to the nearest one, go to the nearest one, and in fact, that's obviously the best solution. Anything else would be backtracking and wasting your time for simple cases. But for a more complicated case like this, where the number tells you the distance, then the greedy algorithm, if you're starting at A, you can go 1, 2, and 3, so you follow 1 and you go to B. From B, you can take 1 or 2, so you go to D. From D, the only one you haven't been before is 5, so it's A, B, D, C, A. And that is total length 9. 1, 2, 3, 4, 5, 6, 7. Let's see, I think I fouled it up. A, B, D, C, A. A to B is 1, to D is another 1, to C is 5, so that's 7, and this 2 is 9. So that trip is a total of 9. But there's a better one, A, C, B, D, A. You go 2 here, B, D, 1 here, and A. That's 8. So the more efficient algorithm involves taking a step right at the start that is not the shortest possible step. That's why they call it the greedy algorithm. The greedy algorithm tries to get the most benefit in one step without looking ahead. But of course, looking ahead a few moves, you might find a better solution. And the same thing would apply to chess or any kind of algorithm like this. You could in chess, you can calculate a numerical value of how good your layout is. And you can do this in bridge, and you could always take the move that maximizes your numerical output. But that's not really the goal of the game. The goal of the game is checkmate. And there can be a route that leads to checkmate that goes through bad numbers. And you'll never find it with the greedy algorithm.
As far as I know, the way Stockfish works, that's the current strongest chess algorithm, is it checks all possible, all the sane moves, so it won't unpurposely check any moves that leave a piece hanging in any way, or you leave a checkmate, but it'll check that move, and it'll check 5 moves ahead of that, and if it sees that path as a valid path, it'll mark it up as a good move.
Yeah, I'm surprised they're not using machine learning yet, but yeah, I mean, the problem is the number of possible moves scales really fast.
Yeah.
So you can't look very many moves ahead before you run out of time and memory.
After the first 5 moves of chess,
Yeah.
there's already like over 2 billion or something.
Oh, yes.
Different possible combinations.
Oh, yes. So looking through all possible moves right to the end would be the best, but there's no way you could ever have enough computer or enough memory to do that.
Yeah, no, it only ever goes like 5 to 8 moves ahead.
So an interesting question is, how do humans do it with their incredibly weak brains? It takes like several milliseconds for each neuron to do one computation, and you only use loops of neurons about 4 or 5 deep to do everything. And that's why, our current programming machine learning algorithms, we're beginning to see what you can do with that. You can do a lot more than you think.
You
Yeah.
think quantum computers can probably correct that?
People have talked about this. Now, until recently, I would always say there's no application of quantum computers in machine learning, but that's coming. In fact, I found an example. Nobody knows. Of course, to be fair, the important thing to know about quantum computers is they don't exist and they may never exist. A record was set last week of Microsoft. See, the problem with quantum computers is each bit is a analog measure. It's not just a 1 or a 0. A qubit is a floating point number from 0 to 1. And the problem is you need it to be accurate. And the current qubits are very noisy. And if they're noisy, your algorithms get nowhere really fast. So Microsoft found a way to implement error correction, which could take hundreds or thousands of physical qubits to make one virtual qubit, and get it down to only 4 qubits to make an error-corrected virtual qubit. So in the most powerful machine they could find, which has 56 real qubits, they were able to make 12 error-corrected qubits. And the number of qubits it would take to do anything remotely interesting is like 1 million. So we're nowhere near having real quantum computers that can actually do anything even close to what normal computers can do. The only point is, if they get 1 million times better than they are, then we'll be able to see exciting new things happen. But that's probably decades away at the normal rate of progress. But you're always guessing about the future. And another guess, by the way, is how much ahead the classified industry is. The Department of Defense is typically 20 years ahead of all unclassified stuff. They had public key encryption for 20 years and kept it a military secret until it was independently invented on the outside. So they might have a working quantum computer behind the veil of classification, but I kind of doubt it because I think it's more than 20 years away. But it's only a guess. Those of us without access to the classified intelligence are only guessing what those guys have. Remember, when I was a kid, people were paranoid, and the hippies said, you got to turn off your TV, you got to unplug your phone, the man is listening to everything you say. And I laughed at him. It turned out that was pretty much true. The man was, in fact, listening to everything we said. I thought they were paranoid nuts, but just because you're paranoid doesn't mean you're wrong. Anyway, so here's another example of another problem, the knapsack problem, essentially, which is mathematically identical to the traveling salesman problem. You want to make change. So you have dollars, 1, 2, 5, 10, 20, and 50. You want to pay $29. In the greedy algorithm, you're trying to pay with the smallest number of bills. In the greedy algorithm, you always use the largest bill. So you're paying $29. First you pay 20. Now you got 10 left. You have 9 left. So you pay with a 5 and then 2 2s. And that, it turns out, is the best solution. You cannot make $29 with less than 4 bills. But if you have a different situation, if your bills are 1, 14, and 25, and you want to pay 29, now the greedy algorithm would start with 25 and then have 4 1s, but there's a better solution, 2 14s and a 1. And that's the problem. You'd have to be smarter than to take the first step that does not take you the maximum distance directly to the goal. So, and this happens in a machine learning algorithm. I got it in my machine learning class. If you run a greedy algorithm, you can ask it a question, it gives you an answer, but the answer never varies. It's always exactly the same. It always takes the most probable word at every step. And they deliberately add random variation to it to make it more like a human would talk and to make you give you a variety of different answers. So here's another shortest path problem. The possible paths from A to D, you could go straight, and that would be 9. You could do A, B, C, D, and that would be 5, 2, and 3, that would be 10, and so on. The shortest one is A, E, F, D, down the bottom, 2, 3, and 2. So you represent it, and in your book they do it by nested dictionaries, which is kind of fun. You make your graph a dictionary, and then inside there you have a graph for each letter, and each one of these has another dictionary, which is how the distance it would take to go to the remaining vertices. And that's a reasonable data structure to encode that problem. And then you can make a table of the shortest distance and go step by step to see how it goes. So A to A is none. In my initial table, just showing, initially I haven't traveled anywhere from A, but after I visit node A, then I could get to B in 5, I could get to D in 9, I could get to E in 2, and so on. So you have a table here. You kept track of the previous node and the distance to the next one, and you just keep updating that table. So after visiting node E, here's the next node you could get to, and you slowly color it in and choose the best of the whole table. This is a way to find your way to the best algorithm, to the best solution. And you can code all that, but again, it's a recursive function essentially. You just have to lay it out so you do the same operation over and over. All right, so let's try some Cahoots. see we're on target here. It's these ones. Oh, and let me check and see if there's comments in the Twitch. There are none. Okay, fair enough. All right, so which one of these has log n complexity? Binary search, we keep splitting in half, of course. Now, by the way, I think I forgot to mention this thing here is Ch3's algorithm, I think. Yep, but not even in its notes. Pretty sure that's what this thing is, Ch3's algorithm. Don't have the name of it in my... There it is. Yep, don't seem to have that name anywhere, but I think that's what it is. I forgot to mention that. All right. All right. They try every possible password. What's that? Yep, that's brute force, of course. All right. And by the way, you can't do a binary search on a thing like that because when you log in, it doesn't say, oh, your password was too small or your password was too big. Now, if it did, you could do a binary search. And that, by the way, is what happens with the padding oracle attack on encryption. You get a clue from your wrong guess that narrows the case. This is what broke a lot of things like wired equivalent privacy, the wireless encryption scheme we used before WPA. If you have information leak that gives you a clue what's wrong, then suddenly it gets much, much easier to break in. All right, which one has n log n complexity? It has to do log n splits. It has to do splits, and that's ordered log n, but it has to do merges of every one of those, and they're n. So it's n times log n. All right. What names you're using there in the names field. All right, let me stop this recording.